Hey there, all right. Let's program something stupid. Today, I'm going to try out the decimal to binary input routines for the Bendix G15, a vacuum tube computer from the 1950s. Going to take a look over here. We have some input-output routines, binary to decimal. I've already actually copied that down and tested it out, but today we'll be doing decimal to binary. Come back here and look at some descriptions of these routines. A subroutine consists of a binary to decimal subroutine, a decimal to binary subroutine, and an output subroutine. The first two are standard conversion routines with normal entries and exits as described on their specification sheets. So I think we'll go look at the specification sheet. What are we looking at here? Did I find the right one? Nope, I skipped a little too far ahead. Here we go, decimal to binary. Fixed point, single precision, runs on command line number 2. Got our entry and exit times, scaling, and then our input. Some value X comes in ID1 as a 7-digit end sign. We put our return jump address into the accumulator, and the returned value is going to be a binary fraction in MQ0 and a binary integer in the accumulator. I see these plus minus absolute value of X and then a second plus minus. I'm a bit curious what that means, but we'll find out. It executes in 5 revolutions. Binary to decimal, decimal to binary. All right, so here is our original G15 source code. I have already sort of baked this ahead of time and had the clanker, ChatGPT, do the OCR for us. Scrolling down here, I've got my input-output routine, decimal to binary. This was prepared by Ed Williams in 1957. Here's that same rough description of it, and then the code from the other sheet. I've already gone back and forth a couple times, making sure each digit is transcribed roughly correctly, but we'll find out if it works or not in a few. If we take another look over at the PDF, after the source code comes a bunch of constants in certain addresses. We can see up here we've got the constants written this way all the way over in the notes column. Down in the second half we've got these constants, and they're instead written over here with parentheses. It's hard to guess if that means something or just two different people typed them up in different manners. Finally, at the very bottom, we've got this extra one kind of snuck in here at address 96 with no parentheses. We'll find out if that's important and if any of these mean different encodings, or, someone came in the next morning and finished typing this sheet out in a different format. Okay, so I'm going to create a new file. I think we'll call it bcd.fraction. This is our decimal to binary, d2b.test.asm. There's a good file name. And we're ready to go. We're going to start typing some code here. I'm going to include my standard Bendix bootloader. At a label CT for count, we're going to choose how many blocks we're going to want to load. Let's think here. This subroutine wants to live on line 2. We also, just for convenience, will put our printout format on line 3, so we'll need to load 3 and 2. We'll load 1, but it'll probably be empty, and then we'll put our test code on 0. So that's a total of 4 decimal blocks. Leave ourselves a little comment. Load 4 blocks of code. All right. Our first block is going to be block 3. Our second block, well, it's going to be block 2. Code under test. Yeah, we'll put our little hash so we can include it right. And what's the name of that again? bcd.fraction. So all right, that'll end up in load 2. Our next tape block, 1. We'll just leave it blank. Who cares? And finally, our last block on the tape. So this is technically a functional program. It's not going to do much, but let's compile it and make sure we haven't screwed anything up here. npm run asm. It's been a minute. We'll make a bootable output, and we'll load bcd.fraction.d2b.tests.asm. A quick run of that, and we see, I'll embiggen this for a moment, a number track to boot, our Bendix loader, block 1, which is our test code. Have I got this backwards? Block 3, block 4. Oh, no, we're all good. We haven't written these yet. Let's stop confusing ourselves here. Block 3, 2. We'll call this line 3, line 2, line 1, line 0. The blocks of code on the tape are backwards from the order they're loaded into lines. It counts down so it can fill line 0 last. That was my bad. It's been a hot minute though. So, all right, let's come up with a format code we want to use. It'll be at block 3, position 03. The value is going to be a binary value, and the way I usually do this is I just start filling it out with zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I think we're going to be able to fit the entire 7-character output in one block. Let's see, 1, 2, 3, 4, 5, 6, 7, with room for, we'll include the sign and a stop. So, all right. Well, now, hop over to the programmer's reference manual and scroll down to somewhere around here where we're going to find our output formats, commands for regular input-output control. As we scroll down, we find our output formats. Sign is 100, digit is all zeros, I knew that off the top of my head, and the stop code is 001. So you all keep those in mind when we pop back over to the code, and we're going to start with a sign. Binary 100, 1, 2, 3, 4, 5, 6, 7 digits, and then finally our stop code, end 001. And we've got these 2 extra little bits hanging off there. That's all good. No complaints. We'll save it and give it another little compile. Pretty happy there. We see our format code up here. Good stuff. Bendix loader. Number track. Bendix loader. Three, two, 1, 0. You know, it's always worth just double checking all of your blocks of code are landing in the correct place. We're not going to worry about that too much, so this time we'll just run this out to d2b.test.pti. All right, and we probably won't be scrolling up and down in the PTI files much more. Cool. All right. Let's figure out how we want to test this code. We're going to start simple, though, and make sure our format code is printing out the way we like. So let's just start right out with our first instruction and decide what we want to do here. Let's just load a value into the accumulator and print it out. We're going to start, as simple as can be and work from there. So our instruction at position 0, we're going to say at time 1, we want to, let's see, what do we want to do at time 1? At time 1, and then we'll go on to 2. So next is 02. We're going to copy from source 0 with characteristics 0 to the accumulator. That's going to be 28. So copy the value at 0001 to accumulator. That's what we're going to do. I'm just going to, shorthand as we go along. What value do we want to put at position 01? Let's just put the value, 4, 20, 69. We can be children here. That's a 1, 2, 3, 4, 5, 6, 7. That's a 7 hexadecimal digit number, all good. Having loaded that into the accumulator, we can print out the accumulator. Let's see, we'll do that at time 02. That's when we said we'd do it. 02. Let's see, nothing interesting there. Output AR to typewriter. We're going to go 02. Let's pull up the actual instructions for that. Might as well show those to you. Type AR. We're looking at that right there. L2N0831. Sounds good to me. L2. So we're at T2. L2 becomes 4. L2 RN. We can just go to time 3 will be our next instruction. Let's see. Characteristic is just how it was over there on the other page. Oh, I'm not showing this to you right now. Sorry about that. We'll switch over to the left screen. So, for 3 characteristic 0, source 8, destination 31, and we'll say type ACC. They call it AR for the accumulator, so let's rename that in our comments. All right, so if this is going to occur at time 4, you might say, hey, shouldn't we be executing our next instruction at like time 5 instead of time 3? Type AR is so slow, it takes multiple revolutions of the drum, so in this case it really doesn't matter, and the next thing we'll want to do at 03 is just wait for IO ready. So await for IO ready. Let's see, we're going to go 03, 03, 28, 31. Wait for IO ready. Oh, that should be a dot. You're right. So anyway, you'll notice this wait for IO ready. It's basically a branch. While IO ready is false, it's going to follow on to the next instruction at time 3. So basically, it's going to loop right back to itself. When IO ready becomes true, it will add 1 to that and take us on to the instruction at time 4. What are we going to do at 4? Let's halt. I'll just do this. Yeah, we're not going to pull up the documentation right now. But the time for a halt is going to be L2, which will turn out to be 06 in this case. Then the next instruction we're just going to say is 04 again. So if we unhalt, it's just going to run itself right back to it, to halt again. O is the characteristic, 16, 31. So it's another one of those special destination 31 commands. So this ought to load this value into the accumulator, type it out, then halt. Let's change this around though. Instead of the halt going back to itself, we'll run back to time 0 if we start the machine again after halting, so we can run the program multiple times. We'll save that, build that PTI, and jump over to the emulator. All right, here we are on the emulator. We'll unload our tape file, choose our file, and find our way in here. G15 tools, programs lib, and here is our d2b test.pti. We'll start that up, and we'll hit this reset button. It loads 2 blocks of tape. I've got the emulator set up to run a little bit quicker, so let's hit go and see what happens. Awesome. 420.0069. You know what? I think for the remainder of this, I'm going to go ahead and run it at real speed. So give me a hot second here to slow this bad Larry down to 1800 RPMs. We'll reload, say hello to Mr. Husky, start the emulator, unload, choose files, d2b test PTI, reset. Now we can see it actually loading those blocks. We'll hit go. So that's more realistic type out speed right there. Good stuff. Maybe I'll scale this up a little, but we can see we printed out our 420.0069. So let's go back to the code and think about what we want to accomplish here instead. We're loading a value, and we're printing it out. Now what we want to do is load a value, convert it from decimal to binary, and then print it out. My assembler already lets us put in decimal constants. So let's think this through here. We want to load a hexadecimal value that looks decimal. So in fact, this 420.69 value right here, let's change it to pi so we don't have to feel like middle school children, huh? 3.14159. 3.14159. Does a 2 come next? Let's say a 2 comes next. So we'll use pi this time. This value looks like pi to you and me, but interpreted as hex, it's some wacky value. We'll take a look at that in a second. So let's save that, rerun our program, head back over to the emulator, start this bad boy up again, bring up this guy, unload, choose files, and we'll load up our test tape. We'll reset, and we'll take a moment to look over here after it runs. Okay, so here's what I want to point out. Right over there, 3.14159. That's the hex value we entered. Once we've converted it to decimal, it's going to look totally different. Maybe we should come up with an approach to know when it's worked right. But we're all good here. Let's just keep going. Back to the code, and we're going to pull this over there so we can find the instructions on how to use it. All right. Input X decimal in ID1, 7 digits, and a sign. We've got this loaded up into AR. We'll just leave those other lines of code somewhere. We can use them later. Well, I've got some nice little functions, features in my assembler where if we know this needs to be L2, we can enter the mnemonic L2 and it's going to calculate time 2 plus 2 and get that 4. And if we leave out the next address, it's going to go on to the next line. Ditto with this halt, we know that needs to be an L2. And our wait for IO ready, these are both L0, L0. And finally, we can even just auto increment these locations. So that's a quick time saver. With the code looking like this, we can move it around in our file and not have to change all of the numbers, because now it's basically the locations and these relative locations will be computed at assembly time. Then go back here, make these same changes if we want, but then here we can even use L2 here. If we save that, assemble it, right screen share, we'll unload this file, we'll just give this thing another run and see what we screwed up. Okay, we didn't screw anything up. That's rare. But now we've got this slightly easier to read code. What are we going to do next? With this loaded into the accumulator, we want to call this conversion function. In order to do that, we're going to have to copy the value into ID1. Where is ID1? This is where I pull over my little printouts, where I have all of the line numbers written down for help. ID is number 25. So at time 01, then we're going to go on to next. We're going to copy from the accumulator with characteristics 0 to 25. accumulator to ID 1. That's the accumulator, the 28. The 25 is ID. 1 is the time. And the 0 characteristic means we're just going to copy it verbatim. We're not going to switch the number representations when we copy over. So, having done that, we need to put a return command in AR. And we also need to figure out how we're going to do that other goto. It's been a while, but let's figure out that first goto to jump into the BCD routine. We'll use that in a second, but that feels a little easier to me. What's that going to look like again? Okay, we need to jump to the entry point, so that's 46.46 dot 2 dot 20.31. So that's sort of our unconditional jump from one line to another line. It's going to set the command line to 2. This 2031 is another one of those special line 31 destination special commands. So this is really a set command line 2 with an unconditional jump to position 46. Go to 46. So that'll take us over there, but once we get to there, it's going to run this conversion routine, hopefully, but then it needs to return, and to be able to return, it's going to have to run a return command, right? So that return command is going to be another one of these unconditional jumps, but we're going to treat it as data. I think you'll see what happens in a second. First, I'm going to write that return command. So that's going to be, do we know where do we want to go? Well, after we do the conversion, we want to type it out. I'm going to create a label, name it AC for after conversion. After conversion, we're going to type out the accumulator, then wait for IO ready and halt. So if that's the case, our address is whatever the value of AC is. So we'll go to AC. It's another characteristic. I've got a typo up here. Don't want to confuse myself. Okay, there we go, source destination. Just said those little numbers backwards. All right, and we're going to go back to line 0, and it's another 2031. So this is go to 0 AC, and we'll just mention that's our return instruction. So we're actually going to treat this like data. How are we going to treat this like data? We're going to load it into the accumulator. So, okay, at time L1, so our next instruction, we don't even have to include that. After that, we're going to go to L2. We're going to load into the accumulator, so we won't mess with it, from line 0 to line 28. You know what we can even do to make this more clear? I'm going to label this return instruction. So we're going to load the return instruction into the accumulator, and I'm going to call this call, and we'll change this to call. Does that look any better? Well, there's a lot of ways to do this. The way I like to do this, if I'm going to do it this way, is after the label, I'll say return instruction. And I'll remind myself that this is data, not an instruction I want to call. And then down here, I'll just sort of describe this label as call conversion routine. We'll even spell return right. All right, so let's review this code for a second, see if it makes any sense. It probably doesn't. We're going to start out by loading the next value into the accumulator. We're going to load 3141592 hex into the accumulator. Then we're going to save the accumulator 2521 to ID 1. Next, we're going to load the return instruction into the accumulator from line 0 into the accumulator, and then go to call. So we're going to skip over this return instruction. Remember, we're treating it as data, not code, and go to this call the conversion routine. We're going to jump to 46.2.2031, we've seen that before. Once we're done with the conversion routine, it's going to execute this instruction. It's going to keep a copy that we passed it in the accumulator, which takes us back to AC on line 0. That's right here. It should type something out and then halt. Make perfect sense? Clear as mud. Let's save this and assemble it. We'll jump back over to the right screen and have a look at what happens. Let's clear our output. We'll unload our tape, choose the file again, reset, stop, and go. This should print out something. All right, fantastic. It printed something out. No idea what this means yet, but our code basically worked the way we expected. We did call that command on line 2, and we got back some answer. What we should see when we run it again, if you watch these command line, it should briefly execute from line 2. In other words, while it's running, this neon should light up. So I'll stop and go again, and we saw that neon flash. Awesome. Good stuff. All right, so what the hell is this value? 2ZYZX8. Well, let's pull up our calculator, our Windows calculator, and find out. We'll throw it back over into programmer mode, and 1, 2, 3, 4, 5, 6. There's a leading 0 we're not seeing. Good stuff. Okay, so we'll type in that 7-digit hex number to Z. Well, that's going to be our F. This is nice. Z is F, Y is E, Z is F, X is D, and then we have an 8. Oh, look at that right there. 3,141,592. So we ended up with a hex value, this 2FEFD8, and the decimal value of that hex value is this pi-looking constant we typed into our code. So we've taken the value 3141592 as basically BCD encoded data, a number that's actually represented in hex only using the decimal digits, that if we were to interpret those digits in decimal, we'd have that value, and we've actually turned it into a full-on hex number that includes that value. So I think we can probably take this and create something a bit more fun. Maybe not much more fun, but let's create a program to help us add. Okay. Let's do some typing. It's been a while, but we ought to be able to do that. It's been long enough that I'm going to have to pull up some example code to look at while we talk. That's okay. How do we do some text input? I'm going to do a little type paste here. Copy paste, rather. All right. We'll talk about this for a second. We're not looking for speed here. We're not looking to optimizations. I'm throwing in a constant right here, ZE decimal 0 for clearing AR. We don't have to do it that way, but that's fine. So just for simplicity's sake, I'm going to start the program with essentially a no op. Just to make our code a little bit easier. So all right, what's this code do here? Load the value at ZE, which was 0, into AR. It's clearing the accumulator. There's another way to do that that's quicker, but we're just going to do it this way because we haven't learned all the commands yet. Now, we copy the accumulator to 23.0 just to zero out line 23. We're going to enable type in, and then we're going to wait for IO ready. At that point, our value will be in, where's it going to be? It's going to be in 23.0. Our value is going to be in 23.0. So let's grab a copy-paste piece of code here that copies that value back into the accumulator from line 23 to the accumulator at time 0. Once again, we're not going to worry about performance here. The drum will go around quite a few times, and we'll have loaded a typed value into the accumulator. Having loaded that value into the accumulator, there's no need for us to load this pi-looking value into the accumulator. So let's throw that away. At this point, we're going to copy that into the accumulator, load our return instruction, and do the rest. Let's give this one a little bit of a spin. We'll jump back over to this screen share, unload the program, grab this, reset our machine, and run. Boop. Those two lights, 8 and 4, indicate that it's awaiting type in. Let's start by doing the exact same thing we did before. So 3, 4, 1, 5, 9, 2. 3 point. Oh, I got that wrong. Well, we'll do it anyway. We'll start over and let's type in the number correct. 3, 1, 4, 1, 5, 9, 2, tab S. All right, that time we got the same value we saw last time. So we're converting values from decimal to hex. Let's give it another spin and let's see. What's a hex number that's kind of fun? Let's put this calculator into decimal mode, clear. And we'll choose, I don't know what we'll want to choose. Let's choose 450. All right. So when I type in 450, we should end up with 1C2. 1, 2, 3, 4, 5, 6. Oh, tab S. You know, we'll make sure. Hey, look, all zeros. Good stuff. 1, 2, 3, 4, 450, tab. And what we're expecting is 1C2. 1W2. Perfect. UVW, because remember we've got Bendix here, Bendix hex here. Nice. What else can we do? We'll clear this. Let's look for hex UVWXYZ. So C0C 3084. 3084, tab S. Wow. All right. This conversion routine's working. We'll pop back to our program here and think of the next thing we want to do. Having run through all this, let's and all that in here. So at this point, we have, we'll just leave ourselves a little note here. The converted value is in AR. Instead of typing it out, let's save it somewhere. Where will we want to save it? Let's just save it in one of our short lines. Let's save it in short line 20, position 0. So 28, 20. AR to line 20, position 0. So we're saving it. Cool. Having saved it, we can copy and paste this code and do it over again. There'd be a smarter way to do this, but that's okay. Just going to grab all of this, copy, paste, and we'll have to make a few little changes. We're just going to be cheap and name all of our things, switch the second number to 2, A2. So let's see, C2, R2, R2, A2, 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 C2 looks good. Change all of our labels, but this time we want to put the converted value in 21. Now we've got both of those, right? Let's do some addition with them. So at 0, 0, we'll copy 20 to 29. So this is going to be 20, 0, AR plus. Oh, we don't want to put it into AR plus. We want to put it into ARC. And then we want to take this, very similar, copy the value at 21, but this time we want to put it on line 29, so that's the accumulator's plus line. We're going to add those two numbers together, and then we're going to type it out. All right. Shoot back over to the emulator screen, clear it, unload the tape, choose a file, dbtest.pdi, reset this troublemaker. All right, get it going. Okay, it's waiting for an input. Let's keep this simple. Let's start with 1 plus 2 equals 3. Holy shit. 1 plus 2 equals 3. All right. Let's stop it and start it. We're going to try something a little tougher. Let's figure out 40. We got to go into decimal mode here. We're going to type in 42 plus 125, and we're going to get a result of 167, so it should print out A7. Let's find out. So what did I say? 42 plus 125. 42, tab S, 125, 125, tab S, U7. That's right. Okay, cool. We've written a calculator where you can enter two values in decimal, and it'll add them together and print it out in hex. All right, let's print it out in decimal, huh? Shoot back over to our other screen, take a look at our code. We'll add a, let's see, and input, convert the first number. Input and convert the second number. All right. Converted value is in AR. I'm going to say add the two numbers. And then we're printing it out, you know, print out AR. And finally in here, we want to take we want to convert back to decimal. All right. Well, let's scroll up and look at this old routine and see how it works. Let's see. Hey, that's pretty similar. Our return command in AR and our input in ID1. Is that exactly the same? Input in ID1, return command in AR. So actually we can do ourselves another little copy paste to save some thinking. We're just going to have to find the right stuff to copy paste. Let's see. Up through A2. Load type value into AR, AR to ID1. Copy pasta, but we'll double check this here. We're going to copy the value in AR, add two numbers in AR, so we're going to convert AR to decimal. AR to ID1, that's good. We're going to have to rename these labels. R3C3A3, R3C3A3, A3. That all looks good. Call conversion routine. D2B conversion routine. And when we come back at A3, which is our return address, we're gonna print to AR. Okay, good stuff. Our call, line 46 is going to be different because this time our entry point, it says over here, is 61. So we're going to do an unconditional transfer to line 2, 61. That'll run for a little bit. At around 63, it'll exit. It'll do our little exit command here, which will take us to A3 and print out AR. We'll save that. Run this, and jump back to our emulator screen. Choose Files, load it up, reset, and start it up. Okay, it's waiting for some input. Let's try the exact same thing. And we got a 7. That doesn't feel quite right, does it? We'll add 1 and 1. And we get a 0. We'll add 10. And 10. Well, I'm not liking this, but that's okay. Let's figure out what is going on here. It's always good to first just jump right back to the code. I feel like we were getting the correct value in AR here. Oh, you know, I'm using the fractional code, not the integer code, to convert back to decimal. Well, that's annoying. Let's not do that right now, huh? Ooh. Or we could do everything fractional. Let's think about that for a second. Okay, we're going to leave that printout here, and let's go look at our documentation. It puts a binary integer in the accumulator, but it puts a binary fraction in MQ0. So let's make this work on fractional values instead. They're harder to add anyway. So all we've got to do here is, well, when we've got the computed value in AR, copying basically AR0 to 20, 0, we're just going to change that to MQ, which is line 24, converted value in MQ0, and we'll just remind ourselves computed fractional value is in MQ0, and we're going to copy MQ0 to, let's see, to 20, 0. So that's where we're going to keep that. MQ0 and 20, 0. Down here, we want to kind of do the same thing. We're going to grab that for a second. Converted value is in MQ0. We're going to copy MQ0. We want to copy it to 21, which we cannot do in one instruction. So we're going to grab that, leave that here as a comment, and start by copying MQ0 to ARC. And then, at time 1, we're going to copy AR to line 20. So we're accomplishing this move by moving the value into the accumulator and then from the accumulator into the destination. On this first time around, we could do that all at once because they were at the same time. So having done that, we've got our, we didn't even really need to do this because we could have just done it here, but we're keeping the code similar. We're going to add the two numbers into the accumulator, 20, 0, and 21. So this code can stay the same. Then we're going to convert it to decimal and print it out. Cool. All right. Let's look over here. Unload it. Choose our file. Reset. I'm going to clear this output while we're here. And let's run it. Okay. Let's start with something simple. Let's do the decimal point's meaningless, but we're putting it in so we can see it. 0.05. So we're going to take 0.5 and let's do 0.025. Okay, nice. We got 0.75, so we've successfully performed that addition. We ought to be able to do, we'll try something else. Let's do 0.1, 2, 3, 4, 5, 6, 7 plus point. Nice. That's exactly what we would expect. So we've made sure at this point that this decimal to binary conversion routine does work correctly. It's unfortunate that I don't right now have an integer version of the binary to decimal. We could make a slightly nicer looking calculator, but that's not a big deal. You know, we can work in this little fixed point world. I suppose we can try one more little. Let's do 0.0420 plus 0.00069. Right back to grade school. 42068. So there we're seeing some precision getting lost in the fractional binary to decimal routine, but that's approximately correct. We wanted to see 42069, we got 42068. What you gonna do? The computer's 70 years old. All right, let's just put this to bed with a comment. A simple decimal fraction addition routine. We'll also just call this world's crappiest calculator. Save that. Check it in. Commit and push. You'll be able to find this on my G15 tools GitHub page. Programs, lib, and here is our BCD fraction D2B test program. All ready to go. What the fuck, right? Go program you some old computers.